Good evening, everyone. Today is the last tutorial session and the eighth class of the tutorial session on petroleum technology course by Professor Sonali Sengupta. So let me share my screen first. Is my screen visible? Okay. So let us start with today's session. So today we will be talking about thermochemistry, different uh, terms related to thermochemistry, different components related to combustion and requirements in combustion of a fuel. Till now in this course, we studied about the various processing. In Mainly, we studied about the crude oil, its processing, and as it's not a single component, we know that it requires a uh, complex procedure. Mean not a single procedure, but a number of procedures to get to extract the uh, useful product out of it. And after that, also after extraction of the product from the crude oil distillation and crude oil processing, after that also there are numerous procedures, numerous processings done, numerous additions done, and numerous blending, compatibilizing, and all other things are done with this product to make it suitable according to the make it suitable with the uh, 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 market specifications. Okay, just a second. Make it compatible with the market specifications. So after studying all those, we will be now talking about the. Just give me a minute. Just a second. Someone is trying to join, I guess. So today we will be talking about thermochemistry. So firstly, in thermochemistry, we will be studying about the combustion. So the basic combustion elements in solid and liquid fuels, as we have studied about both liquid fuels as well as solid fuels, as well as the gaseous fuels. So the main combustion elements in solid and liquid fuels, they are carbon, hydrogen, and sulfur. Okay. These are some of the main components which are combustible elements which are responsible for the combustion of, which are released during the combustion of, or basically which are responsible for the combustion of solid and liquid fuels. Okay, the combustible elements, combustible components of gaseous fuels. These are for the solid and liquid fuels, and for gaseous fuels, there are some more added to these hydrogen, then carbon monoxide, then methane gas, CH4, then some unsaturated hydrocarbons, mainly olefins, and if some triple bond hydrogens are, triple bond hydrocarbons are present, then they are also responsible for. They are also combustible components of gaseous fuels. Okay, the combustion procedure is always exothermic. You might be knowing combustion is always exothermic. What is exothermic? It means it liberates energy. Okay, liberates heat. Sorry, it liberates heat. Means it releases a large amount of heat. That is the exothermic. During combustion, a large amount of heat is released and it liberates heat. The combustion reaction may be written as. This is a general combustion reaction, that is a fuel in the presence of oxygen or air. Mainly it is oxygen. If we give pure oxygen, then the combustion, complete combustion takes place. But if we give air also, then in air it is 21% oxygen is present. So in the presence of air also combustion of fuel can take place, but that is incomplete combustion. For that purpose only, we need to provide excess air if we provide air in place of oxygen. Okay, produces the products and some amount of heat. Okay, some or large amount of heat. Combustibles in solid and liquid fuels are expressed as in solid and liquid fuels. Combustibles are expressed as the elements in weight percent, whereas in the gaseous fuels it is expressed in volume percent or mole percent. Okay, the composition of the products of combustion are mainly, they are called the flue gas, is first calculated, and as they are produced and expressed on a dry basis. Why so dry basis? Because this during the combustion flue gas is produced. Why it is called flue gas? Because where it is, when the combustion of a fuel takes place, the gases which are the emitted out of the during the combustion, they are passed through a duct which is called the flue duct, and from the flue duct it passes to the stack to be released out into the atmosphere. Okay. So these flue gases, they are first, the composition of these flue gases are first calculated, and it is expressed on a dry basis. Why a dry basis? Because during the combustion, some amount of moisture is also released. Water vapor is also released. So exclude, you cannot include that water vapor in the flue gases. So the composition of flue gases, it is expressed on a dry basis by excluding out the moisture. Further, the sulfur dioxide and carbon dioxide are reported together as CO2. Sometimes this sulfur dioxide and carbon dioxide, they are collectively reported as CO2. Why so? Because they are extracted, they are removed by solvent extraction, and they are mainly removed in a same solvent. Mean they both are soluble in the same solvent, so they are extracted out using a single solvent. Okay. Coming on to theoretical air, as here I told that for the combustion, oxygen is the requirement, but it is possible that we take the pure oxygen, or it is also possible that we take air. But in air, as we know, the component of air, it is oxygen 21%, nitrogen 79%, along with the traces of some many other elements. We are not concerned right now about all those elements. So, as air consists of only 21% oxygen along with nitrogen, so during combustion, if he uses air, then there are two terms involved, which is the theoretical air and excess air. So what is theoretical air? Theoretical air is basically the amount of air if we introduce the air according to the stoichiometry. If we write a combustion equation, suppose we write a combustion equation as here, this is a fuel plus oxygen. If we write it like this, fuel plus air gives product plus heat. Okay. Then here, according to the stoichiometry of this reaction, if we take air, then that is the theoretical air. It's the amount of air stoichiometrically required for the complete combustion. Stoichiometrically required for the complete combustion of the combustibles. Okay, for complete combustion, the amount of air which is required for the complete combustion of air, that is called the theoretical air. Theoretical products of combustion refers to the flue gas or exhaust gas obtained by the complete combustion of the fuels using theoretical air. Okay. Apart from that, there is another term which is the excess air, because uh, as we know, if we take air according to the stoichiometry, it is impossible for complete combustion of the fuel to take place, because the amount of air, mainly only air is required for combustion in if mainly only oxygen is responsible for combustion. If we take air also, it only uses amount of oxygen present in the air for combustion. So if we take the air according to the stoichiometry, then obviously the amount of oxygen will be lacking for complete combustion of the fuel. So for that purpose in the industries, normally more than the stoichiometrical ratio of the air is taken. Okay. So that is called the excess air. Excess air is the amount of air used in excess of the theoretical and expressed as the percentage of fraction of the theoretical air. It is expressed as a percentage of fraction of the theoretical air. Okay. Useful basis of calculation. For all the calculation, we take a basis which is mostly in the cases of solid or liquid fuel, it is 100 kg of solid and liquid fuel. And for gases, it is 100 kilomole of gaseous fuel, or sometimes it is also taken into the in uh, like 1 meter cube of gaseous fuel, mean depending on what kind of basis or what our requirement is. Okay, usually air is assumed dry and carbon dioxide free in combustion calculations, and normally for the for uh, mean for eliminating the complexity, we take the air is almost assumed dry and carbon dioxide free. Okay, in dry air, the volume ratio of the components. In dry air, these are the volume ratio of some of the common components. Oxygen to nitrogen ratio. Oxygen is 21, nitrogen is 79. So 29 by 79, it is 0.27. Okay. Oxygen to air, oxygen is 21 and air we are taking as 100, that is 0.21. Nitrogen to air is 79 to 100, it is 0.79, and for air to oxygen, it is 100 by 21, which is 4.27. Okay, 4.76. Hello, 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 hello. So coming on to the stoichiometric ratio, the ratio of actual air to stoichiometric air, it is called the stoichiometric ratio. Okay. So this is the actual air to stoichiometric air. This is called the stoichiometric ratio, and excess air is actual air minus stoichiometric air upon stoichiometric air. Okay. And excess air is by this we can say it is stoichiometric air minus 1 into 100. Okay. Which gives the stoichiometric air percentage. Sorry, this is stoichiometric ratio minus 1 into 100. Okay. Suppose we take 20% extra air. So the actual air given is 120. It is 100. Okay. Then actual air is 120 minus 100 upon stoichiometric air, that is 100. Okay. So it will be 120%. 20 by 100 into 100, that will be 20% excess air. Okay. Coming on to one of the numerical problem, let us solve one of the numerical problem related to this. Determine the flue gas analysis and air fuel ratio by weight when a medium viscosity fuel with 84.9% carbon, 11.4% hydrogen, 3.2% sulfur, 0.4% oxygen, and 0.1% ash is bond with 20% excess of air. Here, excess air is given as 20%. Okay. assume complete combustion. Okay, we have to assume a complete combustion. So for taking the basis, suppose we take a basis of 100 kg fuel oil. Okay, no change in the basis of expression is necessary, and the data of the ultimate analysis are converted into kilomole. Okay, so let us make a table where we are taking columns as one column for element, then for kg per 100 kg of fuel oil. These elements present in 100 kg of fuel oil. Okay. Then the third column is kilomole per 100 kg of fuel oil, mean kilomole of these elements per 100 kg of fuel oil, and then kilomole of oxygen required theoretically per 100 kg of the fuel oil. Okay. So in the question, it is given how much percentage of these elements is given in the 100 in this fuel oil. Okay. So as the basis is 100 kg, so this 84.9% carbon will be 84.9 kg carbon, then 11.4 kg hydrogen, zero point 0.4 kg oxygen, 3.2 kg sulfur, and zero point 0.1 kg uh, ash. Okay, which will be a total of 100. Okay, now kilomoles of these elements per 100 kg of fuel oil, how we will calculate? By dividing these with the molecular weight, molar mass of these elements. Okay, so it will be 84.9 by 12 will give 7.08. Then 11.4 by 1 will give 11.4 by 2. Okay, this is hydrogen, which is 2. It is 5.70. Then oxygen, zero point 0.4 by 16 will give 0.01 kilomoles. And then 3.2 by 32 will give zero point 0.1 kilomole. And ash is not actually included in the combustion reactions. It is not included in the combustion calculations. Okay. So these are the moles which are present in the 100 kg of fuel oil. Okay. Now, kilomole of oxygen required. So how do we calculate the amount of oxygen required for the combustion of these elements? For the combustion of these elements, we need to get the equations required. Okay. For the complete combustion of carbon, what is the equation? Carbon in presence of oxygen will give out carbon dioxide. Then hydrogen will give H2. Okay. Oxygen, it is not involved in the combustion, but it will be minus because this is contributing for the combustion. It is not consuming oxygen, but it is contributing. Okay. Then sulfur combustion will be S plus O2 gives SO2. Okay. So here 1 mole of carbon requires 1 mole of oxygen for combustion. So the similar moles are 7.08 moles will require 7.08 moles of oxygen. Then 1 mole of hydrogen requires zero point 0.5 mole of oxygen. So 5.70 by 2 moles of oxygen will be required for 5.70 moles of hydrogen. Okay, which is 2.85. Then for sulfur, 1 mole of sulfur requires 1 mole of oxygen. So 0.10 mole of sulfur will require 0.10 mole of oxygen. And by adding all this, we will get 10.02 moles of oxygen are required theoretically for the combustion, for the complete combustion of this fuel. Okay. Coming on to the excess oxygen, we gave 20% excess oxygen. So this is the theoretical oxygen. So by including the excess oxygen, what is the amount of excess moles of excess oxygen? So moles of excess oxygen is 2. 10.02 into zero point 0.2, that is 20%, which will give 2 moles of oxygen. Okay. So nitrogen from total air supplied, since air is supplied, then it will contain nitrogen also 79% nitrogen. For that purpose, this is 10.02 moles, which is the oxygen required stoichiometrically. But 120% into 1.2, which is 120%, mean uh, as 20%, 20% extra, 20% excess oxygen is given. So total air is 120% into 3.76, which is the nitrogen to oxygen ratio. 79 by 21, which is 3.76. So this is the air. This is the oxygen. Oxygen will be cut by oxygen, that is 21. And we will get the amount of nitrogen, which is 45.25 moles. Okay. Now coming on to the flue gas analysis, what are the components which are involved in the which are present in the flue gas? Carbon dioxide is present, then water vapor is present, SO2 is that sulfur dioxide is present, then nitrogen is present from the air, as well as some amount of oxygen is also present since we provided 20% excess oxygen. Okay. So these are components which are present. So this is the moles of carbon dioxide, as we can see here. These are the moles of carbon dioxide. Then water vapor produced is 5. Water vapor produces 5.7. Sorry, this will be here 11.4 only, 11.4 by 1. And 11.4 moles of hydrogen will need zero point 0.5 moles of oxygen. So it will be 5.7 here. Okay, this will be 5.7. So it is 5.7 moles of water vapor, then zero point 0.1 mole of sulfur dioxide, and nitrogen is here calculated 45.25, and here 2 moles of oxygen are excess. Okay, as we have calculated here, this is 2 moles of oxygen extra. And total moles are 60.13 moles of flue gas. Okay. Now volume percentage as produced, it will be calculated as 7.08 by 60.13 into 100. So we will be getting 11.78. Then here 5.7 by 60.13 into 100, it will be 4 point, it will be 0.17. These are somewhat written incorrectly here. So 5.7 divided by 6.1, 60.13 into 100 will be, it will be 9.47. So this is written here. Then for sulfur dioxide, it is zero point 0.1 divided by 60.13 into 100, it is 0.17. Okay. Then for nitrogen, it is 45.25 divided by 60.13 into 100, it is 75.25. Then for oxygen, it is 2 divided by 60.13 into 100, which is 3.33. Then 2 divided by 60.13 into 100, it is 3.3%. Okay. So on the dry basis, we will exclude this water, that is 5.7 moles. So it is 60.13 minus 5.7. So total moles is 54.43. So for that, we will be doing now 7.08 divided by 54.43. It is 13%. For water, we will be excluding since it is on dry basis. Then for the sulfur dioxide, it is zero point 0.1 divided by 54.43. It is 0.18. This will be 0.18. Okay. Then for nitrogen, it is 83.3%, 83.1 basically it is, and we will be excluding oxygen also. Okay. So it is 100%. For the air fuel ratio by weight, it is for the air, we will take from this, that is 10 total oxygen. Stoichiometric oxygen is 10.02, 10.02 moles into 1.2, which is the total air, into 4.76, which is the ratio of air to oxygen. So that is 100 by 21, 4.76, and 29 is the molecular weight of air. 100, which is the basis taken, that is the 100 kg of fuel. So it will be given 16.6. Coming on to the next question, calculate the percentage excess air for methane burning. The flow rate of methane and air is given as 25 and 290 millimeter cube per hour respectively. So the reaction taken is 1 moles of methane plus 2 moles of oxygen gives 1 mole of carbon dioxide and 2 moles of water vapor. Okay. So this is taken in the base on the basis of volume percentage. So 1 meter cube of methane requires 2 meter cube of oxygen to give 1 meter cube of carbon dioxide and 2 meter cubes of water vapor. Okay. So taking the basis as 1 meter cube of methane is burning. So stoichiometric air for methane burning required is 9.526. How so? It is 2 by 21. 2 is this is the required. Stoichiometrically, 2 moles are required. So 2 by 21 is oxygen. And okay, so it is 2 by 21 into 100. It is 9.524 meter cube per meter cube. Okay. Assume the flow rate of methane is given as 25 meter cube per second. So for 1 meter cube of methane burning, this much amount of air is required stoichiometrically. So for 25 meter cube, air required will be 25 into 9.524, which is 238.1 meter cube per hour. And the flow rate of air given is 290 meter cube per hour. So this is the air given. This is the theoretical air given, and this is the stoichiometric air which is required. So stoichiometric ratio will be the theoretical air by stoichiometric the stoichiometric air. Okay, so it is that is sorry. This is the actual air which is provided. So actual air by stoichiometric air is the ratio, that is the stoichiometric ratio. It is given as 1.22. So by this only we can calculate the excess air, that is 1.22 minus 1 into 100, that's the 22% extra air is given. Coming on to mechanism and kinetics of combustion. So the mechanism on and the mechanism and kinetics of combustion, the most essential thermodynamic parameter is equilibrium constant as a function of the most essential thermodynamic parameter is equilibrium constant as a function of temperature, which is required for the study of kinetics of combustion reaction. Okay, so the equilibrium reactions for a suppose if we take a reversible reaction, so these are the two rate constants K1 and K2, and for this reaction, equilibrium constant is K1 by K2. So since K1 and K2 are functions of temperature, so automatically equilibrium constant also becomes a function of temperature. But for calculation of this K1 and K2, study of the kinetics of combustion reaction is required. Many steps in the combustion reactions are reversible in nature. Mostly all the reactions are reversible in nature, but for or eliminating the complexity, we consider some of them as irreversible. Okay. The example of some equilibrium reactions of combustion are given here. These are free radical formation reactions. So these will be dots, and this is the termination reaction. The equilibrium constants for the above reactions are KPOH. Why P is taken? Because these are all the gases. So this is the partial pressure of OH. So KPOH is POH, that is the product, partial pressure of product upon partial pressure of reactants to the power their stoichiometric number. Okay. So these are the equilibrium constants for these three reactions. Thermodynamics can describe the composition of the species of equilibrium steps, but and overall mechanism, but it cannot predict the speed of the reaction. Thermodynamics cannot predict the speed of the reaction, so the knowledge of chemical kinetics is essential. Since reaction, since rate constants are a function of temperature, so if we increase the temperature, if there is an increase in temperature of 10 degrees, then the reaction speeds up twice. Okay. So, but we cannot determine the speed of the reaction by equilibrium steps. For that purpose, chemical study of the chemical kinetics is essential. A combustion reaction has a particular speed at a particular temperature. Okay. In many cases, the mechanism of combustion follows the complex kinetics phenomena with several elementary steps. The combustion can be explained by radical mechanism. By a free radical mechanism, the combustion can be explained usually consisting of 3-4 steps, that is initiation, propagation, branching, and termination. It can be explained by the combustion of methane. So here the combustion of methane is expressed in 4 steps, that is the initiation and the initiation of the initiation step, dissociation of the methane into two ions, mean two free radicals, methyl radical and hydrogen radical, hydride radical takes place. In the second step, these radicals join with another methane molecule to further propagate the reaction, further increase the increase the uh, molecular weight of the compound to produce heavier compounds. So chain propagation takes place. Further, sometimes branching also takes place by addition of two different radicals or some unreactive component also, as here carbon monoxide and oxygen is taken along with the radical. And in the termination steps, two radicals along with the non-reactive species may react to give a stable compound along with the along with the radical. Coming on to the second part, which is the flame. If the what are flames? So if the combustible substances they produces vapor during burning, a flame is produced. Okay, if the combustible substances when they are combusted, if they produces vapor, then flame is produced. So what is flame? It is a luminous zone of rapid exothermic reaction in combustion of vapor with the formation of light and heat energy. Flame is a luminous zone which produces light and heat energy Luminous zone because of the rapid exothermic reaction taking place in the during the combustion of vapor. It is followed by a non-luminous zone which is appeared just after the flame where the temperature is slightly reduced. Okay, so after this glowing flame region, there is this non-luminous region also after this luminous region. The flame is bound between a gaseous zone and a non-luminous gaseous zone. A gaseous zone where is mean a gaseous zone where this suppose this is the light zone. After that, this is the dark zone, non-luminous zone. This is also gaseous zone. This non-luminous zone is also gaseous. Okay, so it is telling that the flame it is bounded is a complete package of this luminous gaseous zone as well as the non-luminous gaseous zone. Okay, the combustion of gaseous fuels in a flame needs the intimate contact of the fuel with the combustion of the gaseous fuel. Uh, in a gaseous fuel in a flame, how a flame is formed during the combustion of gaseous fuel. It is formed by the intimate contact of the fuel with the oxidant. Basically, it is either oxygen or air prior to the reaction. The reaction takes place in a narrow zone within the flame, and this combustion zone is called the flame root, flame front. The reaction takes place in a narrow zone within the flame. The reaction takes place, suppose the reaction is taking place here. So this is called the flame front. Okay. And here the temperature is about to goes to several thousand degrees. Types of flames, coming on to types of flames. Flames may be of different types depending on the extent of mixing of the fuel, and oxidizer, and sometimes how the mixture reached the reaction zone. Okay. The flow pattern in the reaction vessel, such as well mixed and plug flow, are the major tools to classify the flame in different types. The flow pattern, basically the flow pattern of the fuel and the oxidizer, mixture of fuel and oxidizer in the reaction vessel. It may be either it is well mixed, either the fuel and oxidizer is well mixed, or plug flow. Plug flow mainly it means they are not well mixed. They are not well mixed, not pre-mixed. So these mixing also helps in classifying the flames in different types. The flame may be turbulent or laminar type depending on the flow behavior of the combustion gases. Okay. The flames are mainly classified as non-premixed or diffusion flames and premixed flames. These are mainly premixed are like where the fuel and oxidizer gets mixed uh, completely with each other before the reaction, and non-premixed is the where the mixture of fuel and oxidizer does not mixing of the fuel and oxidizer does not happen before the reaction. Okay. Coming on to non-premixed flames, in many combustion processes, the air and fuel are often initially not mixed. Initially, they are not mixed. The fuel and oxidizer are kept on either side of the reaction zone. Suppose this is the reaction zone. So the fuel enters from this side and air enters from this side. Okay, from either sides and move to the reaction zone, and they move towards the reaction zone together. The resultant flame is termed as the diffusion or non-premixed flame. In the laminar flow region, they reach the reaction front by diffusion. Okay, so they reach to the reaction zone where the reaction takes place, reaction front by diffusion before the reaction takes place. Product of combustion also diffuses to come out of the reaction zone, and this flame is called the laminar non-premixed flame or diffusion flame. In diffusion flame, the combustion rate will solely be controlled. In this diffusion flame, combustion rate is solely controlled by the diffusion rate, not by the kinetics of the reactions. Okay. Coming on to the premixed flames, in this the fuel and oxidant gases are mixed together at ambient condition before being delivered to the flame zone. Okay, they are mixed beforehand before entering them into the reaction vessel. Okay, as the mixture approaches the flame front, it is heated by the conduction and radiation. And the heating of the reaction mixture takes place by heating and radiation as it moves forward towards the flame front. Gradually, the mixture is sufficiently heated at the reaction front, and when it gets sufficiently heated up, the chemical reaction takes place. Okay, the turbulent pre-mixed flame plays an important role in the various practical applications. It increases the ignition of the fuel with the reduction in the emission of gases. Okay, The flame speed or the velocity of the reactants in the reaction zone is important. The flame speed or the velocity of the reactants in the reaction zone is important. Both laminar premixed or laminar non-premixed flames are slow processes and non-economical. Okay. Turbulence actually results in a reduction in flame speed. Just a second. Turbulence actually results in reduction in flame length, and the turbulence can be increased by reduction by recirculation of the fuel air mixture. Okay. Turbulence in a combusting fuel causes a significant increase in the reaction rate. Because of the turbulence, the reaction rate will also increase due to the mixing of the hot burnt product gases and the cold unburned reactant gases. If we recirculate the products, then turbulence is created, and but in turn it increases the reaction rate. Okay. Because of the strong effect of turbulence on the flame propagation rate, the coupling of the fluid mechanics and chemical kinetics presents a challenge in modeling the turbulent combustion events. Okay. Coming on to the flame structure, in the premixed type, the laminar flame is the most simplest type. The structure of the flame can be analyzed by a flame in the burner. The most simplest example is the Bunsen burner that you would have seen in your chemical labs. And the idealized shape of the reaction zone of a laminar premix flame, it is a cone. It is basically a cone type structure is the ideal structure for a flame. Okay. The height of the cone represents the flame length and depends on the velocity of the outlet. Coming on to the flame parts of a flame. Flame consists of four distinct regions: zone containing unburned gases, zone containing unburned gases. So this is the zone containing unburned gases. Then the reaction zone. So this is the reaction zone. This is the reaction zone, flame front. Okay. Then the incomplete combustion zone. This is the incomplete combustion zone, and this is the complete combustion zone. Okay. This outer part is the complete combustion zone. Okay. Coming on to the flame propagation. So this is a flame front, which is a stationary thing. It is a flame front where reaction takes place. And this is a vertical line, and this the alpha is the angle between the vertical line and the flame front. And this alpha, it is the unburned gases, mixture of unburned fuel and air. Okay. And Vp, it is the velocity of flame propagation. This is the velocity of flame propagation, which is perpendicular to the flame front. So this Vx, which is the velocity of, uh, since the flame front is stationary and the velocity of flame propagation Vp with respect to the unburned mixture will be equal, this Vp will be equal to the flow velocity of the unburned mixture and normal to the flame front. This is called the burning velocity. Okay. So this Vp is equal to Vx sine alpha. And alpha is the flame cone angle and Vx is the velocity air fuel mixture, velocity of the air fuel mixture. Okay. And velocity of flame propagation depends on the fuel air mixture, properties of the fuel air mixture, pressure and temperature of the process. Okay. Now coming on to the flammability limit. The flammability limit refers to the range of compositions for fixed temperature and pressure. Okay. Flammability limit is basically the composition, that is the composition of mixture of fuel and air at, at a definite temperature and pressure within which an explosive reaction is possible. Okay, so there is this scale where different compositions of fuel plus air mixture, different composition of fuel plus air mixture is there, and at different temperature and pressure, this scale has different composition of fuel and air mixture. And suppose this is the limit, this is the lower limit, this is the upper limit. So within this limit, combustion can take place, flame can form. Apart from that, mean after that and before this lower limit and after this higher limit, there will be no ignition. So means no combustion will take place even if an external ignition source is introduced. Okay. The flammability limits describes the range of fuel concentration in terms of volume percent, and this reaction may occur even when the mixture is cold. And if within this range, concentration of the fuel and air mixture is there, then even if the fuel is cold, then also the flame will form. Okay, the flammability limit also depends on type of atmosphere. For example, limits are wider, much wider in the case of oxygen than in air. Okay, which is quite obvious because oxygen, it is purely oxygen, 100% oxygen, whereas in air, along with oxygen, nitrogen is also there. Okay. A mixture that has less than a critical amount of fuel is known as the lean or lower flammability limit, or greater than a critical amount of fuel, it is the upper flammability limit or rich fuel. Thermochemistry, then coming on to the third part, which is the thermochemistry. It describes the thermal behavior of a reacting system. Okay, so what is thermochemistry? It describes the thermal behavior of a reacting system. The heat energy generates from the combustion of a fuel with air, where the internal energy of the fuel species is the chemical energy. So, when a fuel is combusted, so this internal energy, that is the chemical energy stored in the fuel, it in the presence of air, it combusts and converts this chemical energy into heat energy. Okay. This energy is associated with this chemical energy is associated with the chemical bonds and intermolecular attractions which are present in the fuel structure. Then during chemical reactions, some chemical bonds are broken with the formation of new chemicals and with the transfer of some of heat between system and surrounding. Okay. So the heat of reaction, it is the quantity of heat exchange between a system and surrounding during a chemical reaction at a specified temperature. And the heat of combustion, it is basically the quantity of heat released, because combustion, it is an exothermic reaction, so all time heat will be released. So it is the quantity of heat released in combustion of a fuel with oxygen. Okay. Now coming on to the most important state function. So state functions are basically the properties which remain same at the initial and final point, and it does not affect. Mean the path followed from the final initial to final point does not affect the properties. Okay, so mainly the most important state function related to a chemical reaction system, it is enthalpy. Enthalpy is usually evaluated at standard state, 1 atmospheric pressure and 298 temperature. That is 25 degrees C temperature. This property is used to evaluate the heat or energy evolved or absorbed in a reaction. The enthalpy of an element at standard state is assumed to be zero. Mean absolute enthalpy you cannot calculate. You can only calculate the change in enthalpy. Okay, cannot be evaluated. Quantity of heat released during combustion of a fuel depends on the enthalpy of the fuel. Oxidant related to that of the depends on the enthalpy of the fuel, and oxidant related to that of the enthalpy of combustion products, carbon dioxide and water. So basically, it is saying that the quantity of heat released, it can be given as enthalpy of products, enthalpy of reactants minus enthalpy of products. Okay, it gives heat released. Okay, coming on to adiabatic flame temperature. So what is this adiabatic flame temperature? The temperature of a product in a adiabatic combustion of fuel without applying any shock work. So basically, if the temperature of the products in an adiabatic combustion, if we combust a fuel, if suppose we take a fuel and combust it in a closed chamber, mean closed system, where there is no exchange of heat or loss of heat or gain of heat, then what will happen? The combustion of the fuel will take place, and effluent flue gases will be evolved out. So what will happen? And flame will be flue gases will be evolved out. So as there will be a huge amount of, as it is exothermic reaction, huge amount of heat will be released. But as it is adiabatic system, then it won't be able to. Heat will not be given out from the system. So what will happen? This heat will be taken up by the product gases, and which will increase its temperature. In that case also, the temperature of the flame will also be increased. Okay, so the temperature of the products in an adiabatic combustion of fuels without applying any shaft work is defined. It is defined as the adiabatic flame temperature. So the adiabatic flame temperature is higher, much higher compared to the simple flame temperature when the combustion takes place in the open atmosphere. Okay, why so? Because in adiabatic system, all the heat released during the combustion, it will be taken up by the product gases only. That will increase the temperature of the product vessel. Okay. So in the combustion process, the heat produced during the exothermic chemical reaction is released to their products, and the temperature of the product is raised. Okay, as I told, the temperature of the product will be raised by the heat released during the combustion. So there is no possibility for heat dissipation, no possibility for the dissipation of the heat to the surrounding, and the process will be adiabatic, and there is no heat loss to the surroundings. Okay. As a result, the temperature of the product suddenly increases and produces a flame. Okay. This will help up, this will heat up the product gases in the flame region, and the temperature rise will be maximum. So the product gases around the flame will start to its temperature will start increasing, and the temperature will reach to a maximum. The highest temperature, it is known as the adiabatic flame temperature. Okay. The temperature rise depends on the amount of excess air used or the air fuel ratio. Okay. The flame temperature has the highest value for using pure oxygen gas. If we use pure oxygen gas, then the flame temperature will be the highest, and it decreases by using air, simply by the fact that air has nitrogen also along with oxygen. But if we use too much excess air, then the flame temperature will be reduced. The elution of air by inert gases or heat loss to the environment may also cause temperature of the products to reduce, and incomplete combustion may take place. And the flame temperature is determined from the energy balance of the reaction at the equilibrium. There are two types of adiabatic flame temperature, that is the constant pressure and constant volume adiabatic flame temperature. Okay. Now coming on to the constant pressure adiabatic flame temperature. So here we can see this is a combustion reaction. This is a closed system where fuel and air is injected, and combustion reaction takes place. There is no loss of heat from the system, and product is given off. From the first law of thermodynamics at constant pressure process, first law of thermodynamics, that is delta Q equals to, just a second. Delta Q equals to delta U, that is the change in internal energy, is equals to QP minus WP, that is QP is the heat added at constant pressure, and WP is the work done by the system, and WP it is P delta V. Okay, so it is taken as P delta V. E and delta H is, that is enthalpy equals to internal energy plus P into V, which is the pressure into volume. So at constant pressure, what will happen to this reaction? It will be converted to delta U plus P delta V plus V delta P. And for constant pressure, this will be zero. So we will be getting delta U plus P delta V. So under adiabatic conditions, under adiabatic condition, what will happen? There will be no heat loss, and the change in the enthalpy will be zero. So change in the enthalpy, if change in enthalpy is zero, then this reaction, it will be zero. Okay. And QP is zero. So for equilibrium reaction, we can say that as change in enthalpy for adiabatic reaction and equilibrium reaction, we can say that as change of enthalpy is zero. So enthalpy of reactant equals to enthalpy of products. Okay. So it will be taken as sigma of enthalpy reactant, that is Ti is the initial temperature and pressure, and enthalpy of product, that is T, that is the final temperature, and this is pressure, which is constant, so it is same. So Ti is the temperature of the Ith component, is the inlet temperature of the fuel and air, and Tr is the reference temperature that is normally taken as 25 degrees C, which is 298 Kelvin. Okay. So this is given as sigma Ni integration T from reference temperature to T, that is the final temperature, Cpi, which is the heat capacity, and it is expressed as AI plus, for it is for example taken as AI plus BIT plus CIT square, and QVL, which is the latent heat of vaporization or condensation for phase change of the product during the change of the temperature from TR to T. So during the change of the temperature or during the combustion, if there is any phase change, then QVL, latent heat of that phase change, latent heat of vaporization, is also taken into account. Therefore, this reaction, if we put this into here, we will be getting this, and it is Q after integration. Okay. Delta HF, it is the enthalpy of formation of the products. And the flame temperature T may be calculated from the previous equation. It is assumed if we normally take QVL as 0, we are considering no phase change. So if mean heat capacity data is given, that is CPI dash bar is given, then this reaction is converted to this. QVL becomes 0, and here T add, which is the flame adiabatic temperature, and this is the reference temperature, which is 25 degrees C. So this is the equation we get. Now coming on to the constant volume adiabatic flame temperature from the first law of thermodynamics, that is QV is delta U, that is the change in internal energy. QV equals to QP minus nRT. From the equation here itself, QP minus WP, which is P delta V, and P delta V is also taken as nRT. So P delta V is taken as nRT, that is taken delta, and delta U, if we take it from here, then it will be delta U minus P delta V. Okay. So here delta H minus P delta P, which becomes nRT. So in adiabatic system, QB is equals to 0 and delta HP. So this delta HP becomes equal to 0. Okay. So if QB is 0, then delta HP minus nRT becomes 0. Oh, and the equation for initial temperature to final temperature becomes this. Okay. And it becomes to 0. And it becomes equals to 0. Coming on to one of the numerical and adiabatic flame temperature, that is, determine the adiabatic flame temperature at constant pressure combustion of propane gas using stoichiometric air. The heat of combustion of propane is 2220 kilojoule per mole. And mean CP, that is mean heat capacity data of at 1200 Kelvin, is given as for carbon dioxide, for hydrogen, sorry, water vapor, and for nitrogen it is given as. So taking the basis as 1 mole of propane burning with stoichiometric air, and the reaction is propane plus oxygen. 1 mole of propane and 5 moles of oxygen gives 3 moles of carbon dioxide, 4 moles of water vapor, and 18.81 moles of nitrogen. How so? This is basically 79 by 21, which is nitrogen, into 5. Why 5? Because here 5 moles of oxygen are taken. So for 5 moles of oxygen, 5, this nitrogen will be 5 times also. Nitrogen will also be similarly taken. So this gives 18.81. So taking this reaction into account, QC equals to sigma CPI minus sigma CPI into TF minus 298. So for for carbon dioxide, 3 moles of carbon dioxide into CPI plus 4 moles of H2O into CP of H2O. Then uh, 18.81 moles of nitrogen into CP of nitrogen. This will be in bracket into TF, which is the adiabatic flame temperature minus reference temperature, which is 298 Kelvin. So we get this, and the heat of combustion of propane is given. Total heat of combustion of propane is given here, which will be equal to this thing. It will be equal to 2220, and we will be getting CFS 2570 Kelvin. So the adiabatic flame temperature is 2570 Kelvin with stoichiometric air. Okay. Now coming on to the fourth section, which is the combustion burners. So air for combustion can be supplied to the burner in sub. So burners are basically simplest form of arrangements where combustion reactions may take place. Okay, so the air for combustion can be supplied to the burner in several ways. Okay, there are two types of airs which can be supplied to a burner. One is the primary air, which is a term used to describe air supplied and mixed with fuel prior to ignition. Okay, so this is usually controlled through orifice. This introduction of air into the burner, it is controlled through orifices and valves where all the combustion air is mixed with the fuel and is ready to ignite as soon as it reaches the burner nozzle. Okay, the term premix is used for burners and combustion systems where the air and gases are mixed prior to the burner combustion. Similar to the one in flame, here also premix and non-mix is there. So sometimes the air and gas or fuel is mixed prior to injecting it into the burner, and sometimes it is mixed at the mouth of the nozzle itself. Okay. When they are mixed at or within the burner nozzle, it is called nozzle mix system. Coming on to one of the type, which is the premix burner. Here, the fuel is entered here and air is entered here, and this is basically the combustion chamber. So there are various premix systems in which the part or whole of the combustion air is mixed with the fuel gas to create an air gas mixture that will effectively burn at the burner nozzle. The air and gas volume flow must be controlled and mixed prior to being piped to the. Mean it is mixed prior to the in prior to the burning of the air gas mixture. So it is injected and mixed here, and then it is burned. Okay, a mixing device blends them to a thoroughly combustion combustible mixture. Sometimes a mixing device is also used for mixing them thoroughly. Coming on to the next type, which is the nozzle mix burners. Air and gas are mixed at the burner nozzle and nozzle mix burners. Okay. So here, as we see, the air is introduced from here and gas is introduced from this orifice. And due to this, only a vortex is created, and this air and gas mixed here. And turbulence is created. It is mixed in this section, and then it is pumped to the orifice. For burning here. Okay. Air and gas are mixed at the burner nozzle in nozzle mix burners. Some nozzle mix burners keep air and gas separated until the point of ignition. Sometimes it is mixed here, okay, and sometimes what will happen? It will not mix until it is reached at the point of ignition. So it will be mixed here in other cases. Okay, it is told here. Whereas others some mix of the primary air prior to the point of ignition. Prior to the point of ignition, that means it will be mixing here, and if it is mixed at the time of ignition, then it is mixed here. Field nozzle mix burner systems depend entirely on primary air. Okay. By contrast, secondary air is supplied to the flame after it is ignited and is brought at the burner. Primary air is that we supply, and second there is also secondary air. What is the secondary air? The air the flame takes from the surrounding air. Okay, so this is the secondary air. If suppose this is here, the flame will be there. So this flame will be taking some amount of air from the surroundings also. That is called the secondary air. By contrast, secondary air is supplied to the flame after it is ignited and it is brought in at the burner. It is simply telling that the secondary air is supplied to the flame after the ignition. Obviously, after the ignition, only the flame can take the air from the surrounding. Okay, an example of both types is in atmospheric burners, which uses about 70% primary air and 30% secondary air. It means that in the atmospheric burners, basically, suppose if we take example of our gas burners, gas stoves in our kitchens, 70% air is given from the given as primary air, and 30% air it takes from the surroundings after burning. Okay. Coming on to the gas burners, it is a device to generate a flame to heat up products using a gaseous fuel. So here in gas burners, simply gaseous fuels is used, such as acetylene, natural gas, or propane. Some burners have an air inlet to mix the fuel gas with air to make a complete combustion. Okay. According to the pressure of the gas supplied to the burner, they are classified into three types: low pressure, medium pressure, and high pressure. And these are the pressures of the three given. The main component of gas burners are the mixers and the burner nozzles. Burner nozzles and mixers are the main component. Why? So, because in the gas burners, the complete mixture, homogeneous mixture of air and fuel should be done. Otherwise, complete combustion of the fuel will not take place, and you will get a sooty flame. Okay. Depending upon the structure of the flame, gas burners may be of the following types. There are different types of burners: torch burners. Each burner, torch burner, it is simply a burner which is giving a one flame, a single flame, like a burner tip, like a torch. Okay. Ring burner, it is mainly an atmospheric burner. Here, burner head is in the form of concentric concentric rings having suitably drilled holes. For example, it is the burners we have in our kitchens. It is simply a concentric ring in which holes are drilled. Gas stove, it is simply like this, na. So this is a concentric ring in which holes are drilled. Coming on to the pipe burner, this is also usually a atmospheric burner. This mixing tube ends in a pipe with drilled holes or projecting tube ports. This may be a single or multi-row drill. Suppose, for example, this is a tube, and from here, fuel and air mixture is introduced. So here, either single holes or multiple holes are drilled on this pipe, from where fuel is ignited. Okay. Flameless combustion types. In the surface combustion system, the combustion is localized on the solid surface and no flame is visible. This system are often referred to as flameless combustion. So due to the environmental concerns of the release of flue gases and emissions into the atmosphere, nowadays flameless combustion of fuel is also becoming very famous. Why? So because if flameless it will be there, then there will be no emission in the atmosphere. So the combustion, it is localized on the solid surface and no flame is visible. Okay. Coming on to the pulsating combustors, the periodic appearance of explosion flames characterized by a typical pulsating combustor. It is basically blinking kind of movement of a flame. It is pulsating combustor. Coming on to the oil burners, till now we talked about the gas burners. Now coming on to the oil burners, an oil burner is a mechanical device that combines fuel oil with proper amount of air before delivering the mixture to the point of ignition in a combustion chamber. So it is a mechanical device where mixing of oil with proper amount of air is done, and then it is delivered to the point of ignition. Okay, it is essential for the efficiency of the combustion process that the oil and air is well homogenized with a few pure droplets of fuel oil. The most important factor is that the uniform mixing of oil and air mixture should be done. Why so? Because if there will be no homogeneous mixing, then incomplete combustion will take place. So in that case, it tells that very few drops of pure fuel oil should be there. Mean all the drops should consist same amount of fuel oil and uh, air. Okay, so the fuel oil burners, either they are vaporizing type, and either they are atomizing type. Fuel oil burners can be in general characterized by gun type, mean when the fuel is burned by the pressure of by atomized using a pressure gun. it is the atomizing type. Then the pot type, it is vaporizing type, where the fuel oil, it is vaporized, and when this vapors of the fuel oil, it comes in forms of uniform mixture with the air, then the ignition takes place. Rotary type fuel oil burner, here force atomization before vaporization. Here vaporization plus atomization, both the procedure takes place together. Oil is atomized by using a rotary cup, rotary disc, and swirling method. Coming on to the swirl oil burner, in the swirl oil burner, the pressurized liquid enters the liquid fuel enters tangentially through the slots at the high velocity in the oil swirl chamber. So here we can see this oil, it enters tangentially into the slots, so tangentially from here, and air is entered from here, and at this point, mixing of this oil and air takes place. It flows in the form of a vortex. This flows in the form of a vortex and escapes through this nozzle at the end of the chamber. Air enters at the this annular space, and moves forward, and the fine droplets emerges at the exit of the chamber in the form of spray. Okay, like this from the orifice, fine droplets of a mixture of oil and air comes out. Pot type burner, it is the most inexpensive and simplest form of fuel oil burners, as we have seen stoves in our houses in old times. And it has the lowest operating cost. In the pot type fuel burner, the fuel evaporates in the combustion air. The fuel evaporates from here, and it evaporates in the burner, and it forms a mixture with the combustion air, and combustion takes place. A disadvantage is that it has the limited capacity, and this type, it is generally used in the smaller application. Rotary cup burner. The rotary cup burner are usually used in the industry as well as for some domestic purpose also. Here in this, the device consists of a rotary cup. This is a rotary cup and a fan which is attached to a shaft. So what happens? The oil droplets from the this cup, it hits on the wall and evaporates, and this fan, when it moves, it sucks in the air and hits that air onto the wall, where that air comes in contact with the vapor of the fuel, and ignition takes place. It burns diesel oil as well as heavy oil at lower temperature and pressures. Okay. Depending upon the structure of the flame, gas burners may be of the following types. Sorry, this is it's repeated. Okay, just a second. Coming on to the fourth section, last section of this course, which is the internal combustion engines. So this is the introduction part of the internal combustion engines. In internal combustion engines, the gas is produced from the combustion of the gaseous or liquid fuel at high pressure. They are expended in a piston cylinder-like arrangement, which helps them to transmit the mechanical energy to the crankshaft. Okay, this we will be discussing in detail. The engines, they are classified into two types: the two-stroke engine and the four-stroke engine. So the process of ignition and mixing of air and fuel are carried out in two different ways: the Otto cycle and diesel cycle. Otto cycle, it is basically the petrol engine, and this is diesel cycle, it is the diesel engine. In Otto cycle, air and fuel are premixed together in the approximate ratio of 15 to 1 in the carburetor, and then introduced into the cylinder for compression. In at Otto cycle, basically the petrol engine, what will happen? We will firstly mix the fuel and air together, and we inject them into the carburetor, and then the cylinder, and then introduce. Then it is introduced into the cylinder for compression. So in this engine, petrol or gas can be used. Whereas when it is injected, then this mixture is ignited by a spark plug, and the flame front progresses across the combustion chamber. Okay, so its another name is spark ignition engine. Petrol engine's name is spark ignition engine. And in the diesel engine, what will happen? Firstly, here mixture of fuel and air is not used. Simply we introduce pure air. It is compressed first and then fuel is injected in the form of droplets at the front of the compressed hot air. Okay. The temperature of the air increases with the heat of the compression and the ignition takes place. This is called the compression ignition engine. This is the diesel engine, which is called the ignition in compression ignition, and this is the petrol engine, which is the spark ignition. Okay. Coming on to four-stroke engines, the four-stroke of engines are as follows. The first stroke, it gives input of the fuel air mixture. In the first stroke, the fuel and air mixture is introduced into the engine. In the second stroke, the compression stroke followed by ignition. In the second stroke, this fuel air mixture, it is compressed, and it is ignited by the spark plug. And the third stroke, it is the expansion by the combustion, by the ignition combustion of the fuel takes place, and the combustion gases are released, due to which the expansion of the combustion gases takes place, and due to this expansion of the combustion gases, this work is delivered to the crankshaft. Okay. Now, fourth stroke, it is the exhaust of the, and due to this expansion, after the expansion, these combustion gases, they are released off as the exhaust gases. Operation of four-stroke engine. The four-stroke engine operates on a reciprocating motion of a piston in a cylinder. Reciprocating motion, that is a to and fro motion, up and down motion of the piston in a cylinder. By the to and fro motion of the piston in a cylinder, the power is transmitted to the crankshaft. By this motion, the power is transmitted to the crankshaft, and the minimum cylinder volume, it is called the clearance volume. When the cylinder is completely released, then some amount of volume is left for sweeping, which is called the clearance volume. When the piston is at the top, and the swept volume, the amount of the volume which the piston has swept, it is called the swept volume. You will see this visually more clearly in the further slides. So this swept volume, it is the total volume minus clearance volume. So here, these are the four strokes of an engine. The first stroke, it is the intake of the fuel air mixture. So intake takes place. This intake of from here, the fuel air mixture goes in. Okay, so here the piston goes in this direction. Okay, when the fuel air mixture enters. Then in the second one, compression followed by ignition. So here mixture is there. So here this will move in this direction, it will go in this direction, and the compression of the fuel air mixture will be compressed, followed by the ignition by spark plug, and further this piston will go back again due to the expansion by the combustion gases. Okay, and the fourth one, then the piston is again released to release out the exhaust gases. Okay, coming on to the operations of four-stroke engines. The first, it is the intake. From here, the fuel air mixture will be introduced. When it will be introduced, this intake, the air will be entered from here, and the exhaust valve will be closed. And further, after that, the air will be compressed. This mixture will be compressed, and it will trigger this spark plug for ignition, and the fuel will be combusted in this section. And after the combustion, the expansion of the combustion gases takes place. So again, the crankshaft moves moves down in due to the expansion, and further after the expansion, these combustion gases, they are released off as flue gases, and the piston is also released off. In the first stroke, the inlet valve opens and oil air mixture enters the cylinder. Okay. When the piston moves the full length of the cylinder, the inlet valve closes. Okay. The mixture, it is compressed by the reverse motion of the piston, which is the second stroke. The air fuel mixture gets compressed. Then, due to this compression, oil is ignited at a high pressure by applying a spark when the piston reaches near the end of the cylinder, which is the top dead end. Okay. When the combustion starts and the gas are starting to expand. After the combustion gases start to expand inside the cylinder. When both the valves are closed, both the pressure and temperature of the gases increase. In the third stroke, the gas expands and the piston moves. The crankshaft starts to rotate, and at the end of the expansion, the pressure decreases. The outlet valve opens to exit the gases from the cylinder. In the last stage, the rest of the flue gases escape from the cylinder and the outlet valve closes. Now, the inlet valve opens for the next cycle. Okay, just a second. Now, coming on to the two stroke engine, it only involves two strokes. Two stroke engine only require two pistons movements, one cycle in order to generate power. So here also what will happen, the inlet here fuel and air will enter. It will go in from here. It will move to the transfer port transfers these gases and mean mixture of fuel and air into the cylinder. So here the exhaust and intake of the gas occurs simultaneously. Both the exhaust and intake takes place at the same time, takes place together. Overall, a two-stroke engine contains two processes. Okay, so the compression process, the inlet port opens. Firstly, the inlet port opens and the air fuel mixture enters the chamber and the piston moves down, upwards. Piston will start moving upward, compressing the mixture, and the spark plug is after the entry of the fuel air mixture. The fuel air mixture reaches here, and the piston starts moving upward, compressing the mixture, and a spark plug ignites the compressed fuel and begins the power stroke. Okay. Power stroke, the heated gas exert and after the combustion, the heated gas exerts high pressure on the piston and it applies pressure on the piston and the piston starts to move downwards and the piston moves downward expansion and waste heat is exhausted from here. Okay. Coming on to the assignment questions. The first question is the definition of theoretical air in combustion is. The answer is the amount of air calculated on the basis of stoichiometric equation on of the combustion equation. Just a second. The answer is C. Considering the incomplete combustion of a fuel having 87% carbon, how many moles of oxygen will be required for the generation of carbon monoxide when no carbon dioxide is produced? Okay. So coming on to this question, so let us first take the basis as 100 kg of fuel. Okay. So in 100 kg of fuel, if it is saying that 87% carbon is there, so 87% carbon, that means 87% carbon, 87 kg carbon is present. Okay. So for incomplete combustion of carbon is required here. So carbon plus oxygen gives carbon dioxide, carbon monoxide. Carbon dioxide, no carbon dioxide should be produced. Okay. So for stoichiometrically, if we take it is 1 mole of carbon and half mole of oxygen gives carbon monoxide. Okay. Moles of carbon present in the fuel 87 by 12, it is 7.25 moles. So 7.25 moles are present in the fuel. 7.25 moles of carbon is present in the fuel. So if 1 mole of carbon requires half mole of oxygen, 1 mole requires half oxygen, then 7.25 moles will require 7.25 by 2 moles. That is 3.625 moles of oxygen. Okay. Okay. Coming on to next question, which is what is flame? Flame is a luminous zone of the combustion reaction. So the answer is luminous zone of the combustion reaction. Coming on to the next question, which is the flow behavior of the fuel oil for producing a laminar flame should be. Answer is the velocity of air and fuel should be low and parallel to each other. Okay. The fifth question, which is the heat of reaction, is defined as quantity of heat exchange between a system and its surrounding during a chemical reaction at specified temperature. Okay. The answer is quantity of heat exchanged between a system and surrounding during a chemical reaction at specified temperature. Sixth question, the enthalpy of an element at standard state is. The enthalpy of an element at standard state, it is zero. Seventh question, which is the find out the wrong answer. Air and fuel are mixed in the Bunsen in the burner nozzle in the burner nozzle mix burner. This is correct. In the nozzle mix burner, pre-mixed air and fuel are supplied to the burner. This is wrong. Pre-mix is not introduced; it is mixed within the burner. Okay. A fuel oil burner works by the mechanism. It works by the mechanism of vaporizing and atomizing oil. Find out the incorrect answer in the four strokes engine. First stroke involves vaporizing the vapor into the uh, vaporizing the fuel in the cylinder. This is the wrong answer because it does not involve vaporizing the fuel. The difference between spark ignition engine and compression ignition engine is in spark ignition the fuel mixture is ignited by a spark, and in the compression ignition engine the mixture is ignited by compression. So this is the right answer. Thank you for your patience. So this was it in this course for this session. Thank you everyone for listening to all this listening to these lectures. So thank you everyone.